Hello, my name is Mohsen Keshavarzian. I'm a cybersecurity researcher and a member of IO Academy. In this project, I focus on large-scale analysis of digital signatures in the Bitcoin network, aiming to detect weak or reused non-Cs, the K values used during ECDSA signing. These vulnerabilities, if present, can seriously compromise private key security. To investigate this, I generated and analyzed millions of synthetic transactions. Using machine learning, especially decision tree models, I was able to identify risky signature patterns that may point to cryptographic weaknesses. The ultimate goal of this research is to develop a smart wallet warning system, a feature that can alert users when a signature appears potentially insecure or reused. Now let's take a look at the dataset used in this project. Each record in the dataset represents a Bitcoin ECDSA signature, and it includes a total of 17 input features, along with one single output label. The output is a binary classification that reflects the effective bit length of the nonce, commonly referred to as K. If the effective bit length is greater than 251 bits, the label is 0, which means the signature is considered cryptographically safe and not easily exploitable. But if the bit length is 251 or fewer, the label is set to 1, indicating a potential vulnerability due to a weak or reused nonce in the signature's randomness. Now, I'll walk you through the 7 key features I carefully extracted from each signature. These features are crucial. They help identify irregularities and detect subtle patterns that may reveal weak nonce generation. 1. Calculating the GCD between R, S, and Z. This step helps uncover hidden mathematical relationships among the signature's core components. If a large greatest common divisor appears, it could be a sign that some values are being reused, or that there's weak randomness in the way the nonce K was generated. 2. Counting effective bits. In this step, we count the number of non-zero bits in each individual signature value. A lower count of effective bits often suggests weaker cryptographic strength and may point to insufficient randomness or entropy. 3. Estimating the bit length of nonce K. By combining the bit lengths of R, S, and Z, we estimate how many bits were most likely used to generate the nonce. If this estimated length is too low, it may indicate a dangerously short or even reused nonce, which poses serious security risks. 4. Computing the S over N and Z over N ratios. These ratios help us understand how small the values S and Z are in comparison to the curve order N. If the ratios turn out to be too small, it could indicate low entropy, biased randomness, or patterns that compromise security. 5. Counting ones and zeros in the bit patterns. This feature examines the binary makeup of each value. If there's a clear imbalance in the number of ones and zeros, it could indicate a non-random or even predictable pattern, something highly undesirable in cryptography. 6. Calculating the Hamming distance between R, S, and Z. This tells us how many bits are different between two binary values. If the Hamming distance is small, it might suggest structural similarity, or even that parts of the signature were reused. 7. Jacquard similarity of bit patterns. This step compares which bits are set to 1 across the different values. A high Jacquard similarity score could be a red flag, pointing toward repeated, non-random, or dangerously similar values in the signature. Together, these features allow us to detect vulnerabilities that might not be visible at first glance, but could lead to serious cryptographic weaknesses if left unchecked. Let's start with the Pearson correlation chart. This graph shows the linear correlation between each feature and the output label. K, bit, or relation, measures the strength and direction of linear relationships. A value close to 0 means there's little to no linear correlation. As we can see, most features exhibit extremely weak correlations with K-jite. Only a few stand out slightly, most notably R1S, which refers to the number of 1 bits in the R component of the signature. Other somewhat noticeable features include R-Z effective bio, R-S effective bits, and GCD-RSZ. However, none of these correlations exceed even 0.01, indicating very weak linear dependency. This suggests that the relationship between the features and the effective bit length of K is likely nonlinear or more complex, and cannot be fully captured using simple Pearson analysis. Next, we look at Spearman correlation. Unlike Pearson, Spearman doesn't measure linear relationships. Instead, it analyzes monotonic relationships by comparing the rank order of values, making it more suitable for capturing nonlinear trends. Here, we observe a different pattern. The feature R1s again appears to have the highest correlation with K-body, even slightly higher than before. Other features like GCDRZ, GCDRS, and R-bitterness also show stronger associations compared to the Pearson analysis. This means that even if the values don't change linearly, they still tend to increase or decrease together in a ranked order. This Spearman view suggests that some features have a consistent directional relationship with K-biz, a useful insight when considering more flexible models like decision trees or gradient boosting. Finally, we come to the mutual information plot. The type tame this level and college variance and Tristan tolls. The Chi-know-this method measures the total amount of shared information between each feature in the target label, regardless of the type of relationship. It captures both linear and nonlinear dependencies, making it a powerful tool in feature analysis. Here we see a clear shift in importance. The top contributors are R1s, S1s, and Z1s, indicating that the bit-level structure of each signature component plays a major role in predicting K-bits. This makes sense as weaker structured randomness in the nonce could directly affect the binary distribution of R, S, and Z. Other features like Hamming RZ, diff-bin, and differences in effective bit length, R-S effective bit, etc., also carry significant information. Unlike the previous charts, this one gives us a more complete picture. It tells us that several features do in fact contain relevant information, even if they don't show strong linear correlations. This confirms that models capable of learning nonlinear relationships, such as decision trees, ensemble methods, or neural networks, are more suitable for detecting weak nonces. Now let's take a closer look at this pair plot, which visualizes 5 of the most informative features in our dataset. Our number ones, the number of 1 bits in the R component, a number ones, the number of 1 bits in S component, Z are number ones, the number of 1 bits in Z on number 1. Hamming R__Z, the Hamming distance between R and Z diffits. The difference in effective bit length between S and Z. Each point in the plot represents a single signature. Blue points indicate K bits equals 0, meaning the nonce appears strong with more than 251 effective bits. Orange points represent K bits equals 1, meaning the nonce is weak or potentially insecure, with 251 or fewer effective bits. Let's break down what this visualization tells us. 1. Overlapping distributions but key differences. Along the diagonal, we see the distribution of each individual feature. At first glance, the distributions of both classes, blue and orange, appear similar. However, if we look closely, we find that in certain ranges, orange points are denser, especially toward the edges. This means that some value ranges are more commonly associated with weak nonces. 2. Clusters of orange-only regions. In several of the scatter plots, we notice something very important. There are regions where only orange points appear and no blue ones. This is a crucial observation. It tells us that specific combinations of features, like Z1s below 100 and Hamming_RZ below 100, may be strong indicators of a weak nonce. In other words, there are zones in feature space that correspond only to insecure signatures. These regions can be extremely useful for creating detection rules. 3. Ideal for rule-based systems or decision trees. Because some regions are clearly dominated by a single class, especially the orange class, this pair plot supports the idea of building rule-based systems or decision tree models. These models can easily learn rules such as, if the number of 1s in Z is less than 100 and the Hamming distance between R and Z is small, then classify as a weak nonce. Such interpretable rules are valuable in building transparent, explainable security systems, especially for smart wallets that alert users to dangerous signatures. 4. The case of diffbit. The bottom row shows the diffbits feature, which has a much smaller range compared to the others. Even though it looks compact, the scatter still reveals some class separability, and in combination with other features, it may enhance prediction performance. Summary. This visualization reveals that while most features have some overlap, there are clear pockets in the data where weak nonces, class 1, cluster together. This supports the use of rule-based detection and adds a layer of interpretability to our analysis of cryptographic risk. In this part of the video, we are building a simple and interpretable decision tree. We use only the most important features, as identified in the correlation and mutual information charts earlier. The tree is trained with a maximum depth of 3 to avoid overfitting and ensure the resulting rules remain simple and understandable. Once trained, we use built-in plotting tools to visualize the tree, showing the decision thresholds, sample counts at each node, Gini impurity values, and how the data is split between secure and weak signatures. This visualization forms the foundation for extracting rule-based logic from the model. Now let's interpret the decision tree and see what it tells us about vulnerable signatures. Root node. The tree starts by evaluating this condition. R1's less than a C 125.5. This means we split the data based on how many 1 bits exist in the R value of the signature. This alone creates a meaningful separation. We're starting with a total of over 37 million signatures. Left subtree. On the left side, we continue with R1's less than a C 120.5. This branch contains about 14.6 million samples, mostly classified as secure. Then we evaluate R bit 246.5. At this point, we reach a pure leaf node. Samples 3,510, class 1. This means all these samples are classified as weak signatures, with k-bits 1. Rule extracted. If R1's less than a C 120.5 and R bit 246.5, then the signature is classified as vulnerable with 100% confidence. This is a powerful and interpretable rule that can be directly integrated into a wallet warning system. Right subtree. Now let's go to the right of the root node where R125.5 and R bit 247.5, then it is always a weak signature. Summary. These results are impressive. With just 2 simple conditions, we can identify regions in the feature space that are entirely vulnerable. No need for complex neural networks. These rule-based conditions are easy to understand, have perfect precision, and can serve as trusted alerts in a smart wallet. This confirms our hypothesis. By engineering strong features and applying decision trees, we can isolate dangerous signature patterns in a cryptographic system. This project marks just the beginning. While we've successfully detected weak signatures using decision trees and rule-based logic, the broader vision goes far beyond that. I'm currently designing a next-generation crypto wallet that integrates real-time intelligence to protect users from multiple types of attacks. For example, it should detect if the wallet is leaked or compromised, identify cryptographic flaws like milk SAD, and warn users when incoming transactions might be linked to AML risks, such as coins originating from suspicious or blacklisted sources. By embedding machine learning and cryptographic rules directly into the wallet, users will gain active security alerts and peace of mind, all in real time. But that's not all. In the next phase of this research, I plan to scan the actual Bitcoin blockchain to detect real-world transactions that match these signature patterns, especially those with weak or reused nonces. This will help validate the model on mainnet data, uncover potential vulnerabilities, and contribute directly to the security of the Bitcoin ecosystem. The journey continues.